What if everything you've ever learned about the universe is built on a foundation that's crumbling beneath our feet? What if the one constant we've relied on for over a century, the speed of light, isn't constant at all? I'm about to show you evidence that will make you question reality itself. In 1999, Australian physicist John Webb discovered something that should have been impossible. He was analyzing light from distant quasars, light that had been traveling through space for billions of years, and he found something terrifying. The fundamental constant that governs how light interacts with matter, something called the fine structure constant, appeared to be different in the distant past than it is today. And if that constant has changed, it means the speed of light itself may have changed. This isn't science fiction. This is peer-reviewed research published in Physical Review Letters, one of the most prestigious scientific journals in the world. And it gets worse, or better, depending on how you look at it. Before we dive deeper into this reality-shattering discovery, do me a favor, hit that like button and subscribe to this channel, because we're about to go on a journey that will fundamentally change how you see the universe. And I'm curious, drop a comment telling me what country you're watching from and what time it is there right now. I want to know where in the world people are having their minds blown by physics. Are you watching this at 3 a.m. unable to sleep? Procrastinating on work at noon? Let me know. Now, let me take you back to the beginning. To understand why the speed of light possibly slowing down would shatter everything we know, you first need to understand just how central the speed of light is to literally everything in physics. The speed of light isn't just another measurement, like the speed of sound or the speed of your car on the highway. It's woven into the fabric of reality itself. When Albert Einstein published his special theory of relativity in 1905, he made one assumption that seemed absurd at the time. The speed of light is constant for all observers, regardless of their motion. Think about how crazy that sounds. If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing still watching the train would measure that ball moving at 70 miles per hour, 50 plus 20. Simple addition. But Einstein said that's not how light works. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, someone standing still doesn't measure the light going 1.5 times the speed of light. They measure it going exactly the speed of light. And here's the kicker, so do you on the spaceship. You both measure exactly the same speed, 299,792,458 meters per second. This isn't just weird. It breaks our intuition about how reality works. But Einstein wasn't just making this up to be difficult. He was solving a real problem that had been plaguing physicists for decades. In the late 1800s, James Clerk Maxwell had unified electricity and magnetism into one beautiful theory. His equations predicted that electromagnetic waves, including light, should travel at a specific speed. But here's the problem. Speed relative to what? When we say sound travels at 343 meters per second, we mean relative to the air. Sound is a vibration traveling through air molecules. But what is light traveling through? Physicists in the 1800s assumed there must be some invisible substance filling all of space that light waves travel through, and they called it the luminiferous ether. Think of it like this. Imagine the universe is filled with an invisible jelly, and light is ripples moving through that jelly. Scientists spent decades trying to detect this ether. They built incredibly sensitive experiments. In 1887, Albert Michelson and Edward Morley conducted what's now considered one of the most important failed experiments in history. They tried to measure Earth's motion through the ether by comparing the speed of light in different directions. If Earth was moving through this cosmic jelly, light should travel faster when moving with Earth's motion and slower when moving against it, just like swimming with or against a current. But they found nothing. No difference at all. Light traveled at the same speed in every direction. This is where Einstein comes in with his revolutionary idea. What if there is no ether? What if light doesn't need a medium to travel through? What if the speed of light is just constant, period, full stop, end of discussion? This solved the problem, but created a much bigger one. It meant that space and time themselves had to be flexible. If the speed of light is always constant for everyone, then space has to shrink and time has to slow down to make the math work out. This is why time moves slower for astronauts in orbit. This is why GPS satellites have to account for relativistic effects, or they'd be off by miles. This is why nothing can travel faster than light. As you approach the speed of light, you'd need infinite energy to accelerate further. The speed of light isn't just a speed limit. It's the exchange rate between space and time. Einstein's most famous equation, E equals mc, has the speed of light squared in it. That equation tells us that matter and energy are interchangeable, and the conversion factor is the speed of light. The atomic bomb works because of that equation. The sun shines because of that equation. You exist because of that equation. So when we talk about the speed of light possibly changing, we're not just talking about light going a little faster or slower. We're talking about reality itself being fundamentally different than we thought. Here's what will blow your mind. The speed of light might not even really be about light at all. Modern physicists think of it as the speed of causality, the fastest speed that information can travel through the universe. Light just happens to travel at this speed because photons have no mass. Anything with no mass must travel at this cosmic speed limit. And here's something even weirder. In Einstein's equations, the letter c represents the speed of light, and it appears everywhere. Not just in relativity, but in quantum mechanics, in thermodynamics, in every branch of physics. It's like the universe's source code, the fundamental constant that everything else is built on. The French physicist Louis de Broglie showed in 1924 that every particle in the universe has a wave associated with it, and the wavelength of that wave depends on c. The German physicist Max Planck showed that the smallest possible unit of action in the universe, called the Planck constant, is related to c. The speed of light sets the scale for everything from the size of atoms to the structure of spacetime itself. So imagine you're a physicist, and you've spent your entire career building theories on the assumption that c is constant. You've tested it thousands of times. You've built particle accelerators that work perfectly based on this assumption. You've sent spacecraft to distant planets using calculations that depend on c being constant, and they arrived exactly on schedule. And then someone comes along and says, what if c isn't constant? What if it's changing? Your first reaction would be to dismiss it. But that's not what happened when John Webb made his discovery, because the evidence was too good to ignore. Let me tell you exactly what Webb found, because this is where things get really interesting. Webb wasn't looking for changes in the speed of light directly. That would be almost impossible to measure. Instead, he was looking at something called the fine structure constant, which physicists represent with the Greek letter alpha. Now stay with me here, because this is crucial. The fine structure constant is a pure number. It has no units. It's approximately 1 divided by 137, and it determines the strength of the electromagnetic force, which is what holds atoms together and allows chemistry to work. The fine structure constant is made up of several other constants multiplied and divided together, including the speed of light. It's like a recipe. You take the electric charge of an electron, square it, divide by the speed of light times Planck's constant times something called the permittivity of free space, and you get alpha. If any of those ingredients change, alpha changes. Webb was studying distant quasars, incredibly bright objects powered by supermassive black holes, and analyzing the light that had traveled billions of years to reach us. When light passes through clouds of gas in distant galaxies, certain wavelengths get absorbed depending on the energy levels in atoms. Those energy levels depend on the fine structure constant. So by looking at which wavelengths were absorbed, Webb could measure what alpha was billions of years ago. And here's what he found. Alpha appeared to be different in the past. Specifically, it seemed to be smaller by about 1 part in 100,000. That might not sound like much, but remember, this is supposed to be constant. It's called a fundamental constant. It shouldn't change at all, not even by a tiny amount. When Webb published this in 1999, the physics community went into crisis mode. Teams around the world scrambled to check his work. Some found the same thing. Others didn't. The debate raged for years and continues to this day. A 2011 study led by Webb and his team, published in Physical Review Letters, used more data and claimed even stronger evidence that alpha varied across different directions in space, suggesting the universe might not be uniform at large scales. But here's the thing. If alpha has changed, what changed to make it change? Was it the electric charge? Unlikely, because charge is quantized and appears in many other equations that work perfectly. Was it Planck's constant? Also unlikely for similar reasons. The most probable culprit is the speed of light itself. Before you think this is just one controversial study, let me tell you about other independent lines of evidence. In 2004, physicist Paul Davies published a paper suggesting that data from a natural nuclear reactor in Gabon, Africa, might show that alpha was different 1.8 billion years ago. This natural reactor, called Oklo, operated through natural nuclear fission. By analyzing the isotope ratios in the reactor remnants, Davies argued that the rates of nuclear reactions back then were slightly different than they are today, which could indicate a change in fundamental constants. Then there's the work of João Magueo and Andreas Albrecht, who in the late 1990s proposed something called variable speed of light cosmology, or VSL theory. They were trying to solve a completely different problem, something called the horizon problem in cosmology, and they realized that if the speed of light was much faster in the early universe, it would solve several puzzles about the Big Bang. Think of it like this. One of the big mysteries in cosmology is why the universe looks the same in all directions. Different regions of the universe that we can see have never had time to exchange light with each other, even in the 13.8 billion years since the Big Bang. So why do they have the same temperature? The standard explanation is something called cosmic inflation, a brief period where the universe expanded faster than light, allowing different regions to be in contact before they were separated. But Magueo and Albrecht said, what if instead of space expanding faster than light, light itself was just faster back then? Problem solved. This is a perfect example of what I call a revelation sandwich. I told you earlier that the speed of light might be changing. Now you understand enough physics to grasp why that's terrifying. Soon, I'm going to show you what it means for your life. But first, we need to go deeper. We need to understand what light actually is, because most people have no idea. You think you know, but you don't. Not really. When I say the word light, what do you picture? Probably sunlight streaming through a window, or maybe a flashlight beam. But light is so much stranger than that. Light is an electromagnetic wave. That means it's a self-sustaining oscillation of electric and magnetic fields. Imagine you wiggle an electron. That wiggle creates a changing electric field. A changing electric field creates a changing magnetic field. A changing magnetic field creates a changing electric field. And off it goes, bootstrapping itself through space, requiring no medium, needing nothing to travel through. Electric and magnetic fields dancing together, recreating each other over and over, propagating outward at 299,792,458 meters per second. That's light. That's what's hitting your eyes right now, if you're watching this on a screen. Oscillating electromagnetic fields trillions of times per second, stimulating the photoreceptors in your retina. But light is also a particle. This is the famous wave-particle duality that quantum mechanics gives us. Sometimes light behaves like a wave, can diffract, interfere, bend around corners. Other times it behaves like a particle of photon, a discrete packet of energy. Which behavior you see depends on how you measure it. This isn't just a quirk of light. This is fundamental to reality. At the quantum level, everything is both wave and particle simultaneously. You are made of wave particles. The chair you're sitting on is made of wave particles. The entire universe is a shimmering ocean of quantum waves, and we're just ripples in that ocean, temporarily organized into patterns that think they're separate from everything else. But I'm getting ahead of myself. Let's stick with light. A photon is weird because it has energy and momentum, but no mass. Einstein showed that the energy of a photon is related to its frequency, how many times per second the wave oscillates. Higher frequency means more energy. This is why ultraviolet light can give you cancer, but visible light can't. UV photons oscillate faster, have more energy, and can damage DNA molecules. This is why X-rays can see through your body, but regular light can't. X-ray photons have even more energy and can pass through soft tissue. The entire electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, is all the same thing, just at different frequencies. Your Wi-Fi router is producing light. Your microwave oven is producing light. Your body is producing light in the infrared. Everything warmer than absolute zero produces light. The sun produces a huge spectrum of light, but our eyes can only detect a tiny sliver of that spectrum, the colors red through violet. Think of it like this. If the entire electromagnetic spectrum were stretched across a football field, visible light would be about 1 yard wide. That's all we can see. We're walking around blind to almost everything. But here's the crucial part. All of these types of light, radio, visible, gamma, all travel at the same speed in a vacuum. The speed of light isn't just the speed of visible light. It's the speed of all electromagnetic radiation. And if the speed of light is changing, then radio waves from distant galaxies would be traveling at a different speed than visible light, which would show up in our observations. Some researchers have looked for this. So far, they haven't found convincing evidence of different speeds for different wavelengths, which actually makes the story more complicated, not simpler. Let me pause here for a second and ask you something. Are you starting to feel that cognitive dissonance? That uncomfortable feeling when new information doesn't fit with what you thought you knew? Good. That means you're really learning. That feeling is your brain reorganizing itself, building new neural pathways. Lean into it. And if you're enjoying this journey, hit that subscribe button, because we're only 15 minutes in and we have so much further to go. I promise you, by the end of this video, you'll never look at reality the same way again. Now, let's tackle the big question. How do we actually measure the speed of light? Because if we're going to talk about whether it's changing, we need to know how we measure it in the first place. The first serious attempt was by Danish astronomer Ole Rachmer in 1676, was studying the moons of Jupiter and noticed something odd. The time between eclipses of Jupiter's moon, Io, seemed to change depending on where Earth was in its orbit. When Earth was moving toward Jupiter, the eclipses came earlier than predicted. When Earth was moving away, they came later. Rachmer realized this was because light wasn't instantaneous. It took time to cross the changing distance between Earth and Jupiter. His estimate for the speed of light was about 220,000 kilometers per second. Not bad for the 17th century. The actual value is about 300,000 kilometers per second. In 1849, French physicist Hippolyte Fizeau did the first terrestrial measurement. He shined light through a spinning-toothed wheel toward a mirror 8 kilometers away. The light would pass through a gap in the wheel, bounce off the mirror, and come back. If the wheel spun at just the right speed, by the time the light returned, the next tooth would block it. By measuring the speed of the wheel, he could calculate the speed of light. Fizeau got 313,000 kilometers per second. Even closer. But the most famous measurement came from Albert Michelson, the same guy who failed to find the ether. Michelson was obsessed with measuring the speed of light as precisely as possible. He devoted his entire life to it. In 1926, he built an elaborate setup between two mountains in California, using rotating mirrors and precise timing. His final measurement was 299,796 kilometers per second, just 4 kilometers per second off from the modern value. That's an error of about 0.01%. Extraordinary for the 1920s. But here's where things get really interesting. As measurement techniques got better and better, physicists realized something profound. We can never measure the one-way speed of light. We can only measure the round-trip speed. Let me explain why this is absolutely mind-bending. When you measure the speed of light, you're always measuring it going from point A to point B and back to point A. Even Fizeau's experiment with the spinning wheel measured light going to the mirror and coming back. Why does this matter? Because to measure a one-way speed, you need synchronized clocks at point A and point B. You measure the time on clock A when the light leaves, measure the time on clock B when it arrives, and calculate the speed. But here's the problem. How do you synchronize clocks at different locations? The only way to do it is with a signal. And the fastest signal possible is light. You see the circularity? To measure the one-way speed of light, you need synchronized clocks. To synchronize clocks, you need to know the one-way speed of light. Physicists noticed this problem in the early 20th century, and Einstein, in his brilliance, just made it a postulate. He said, "We define the one-way speed of light to be constant. We assume that light takes the same time to go from A to B as it takes to go from B to A. With that assumption, we can synchronize clocks. This is called Einstein's synchronization, and it's the foundation of special relativity. But mathematically, there's nothing stopping the one-way speed of light from being different in different directions, as long as the round-trip average equals the value we measure. Light could travel infinitely fast in one direction and half speed in the opposite direction, and we'd never know. This isn't just a philosophical curiosity. Some physicists have seriously proposed that the speed of light might be anisotropic different in different directions. If that's true, causality itself might be directional. The future might not be symmetric with the past. The implications are staggering. But for now, every experiment we can possibly do is consistent with the speed of light being the same in all directions. So we stick with that assumption because it makes the physics cleaner. In 1983, something remarkable happened. The speed of light became exact, not measured but defined. The General Conference on Weights and Measures decided that the speed of light is exactly 299,792,458 meters per second by definition. They did this because our ability to measure time had become much better than our ability to measure distance. So they flipped it around. Instead of using a metal bar as the definition of a meter and measuring the speed of light, they used the speed of light to define the meter. A meter is now defined as the distance light travels in 1/299th, 792,458 of a second. This creates a bizarre situation. If the speed of light is changing, we couldn't detect it by measuring the speed of light, because the meter would change to keep the speed constant by definition. Think about that. If light is slowing down, the meter would get shorter to compensate. We could only detect it through other means, like measuring the fine structure constant, which is exactly what John Webb was doing. This is why his work is so important. He found a way to potentially detect something that's literally impossible to measure directly. Let me give you an analogy to make this clearer. Think of the universe as a video game. The speed of light is like the frame rate of reality, the speed at which information updates. Now imagine you're a character inside the game, and the frame rate starts changing. Would you notice? Not if everything in the game sped up or slowed down proportionally. The only way you'd notice is if you had some external reference point, something that doesn't change when the frame rate does. For physicists, those external reference points are dimensionless constants like the fine structure constant. They're pure ratios independent of any units we choose. If they change, something fundamental is changing. And that's exactly what Webb found evidence for. But before we go further down that rabbit hole, we need to understand why physicists have always assumed the speed of light is constant. What evidence do we have beyond Einstein's postulate? What happens if we're wrong? Let me tell you about some of the most precise tests of the constancy of the speed of light. In particle accelerators, like the Large Hadron Collider at CERN, particles are accelerated to 99.9999% of the speed of light. At these speeds, relativistic effects become huge. Time dilation, length contraction, mass increase, all of these effects depend critically on the value of the speed of light. If c were different in the past, or even slightly different at different energies, the particles wouldn't behave as predicted. But they do, perfectly. Every collision, every decay, every interaction happens exactly as Einstein's equations predict. Then there are binary pulsars. These are pairs of neutron stars orbiting each other, at least one of which is a pulsar spinning and emitting beams of radio waves like a lighthouse. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar system and monitored it for years. They found that the orbit was slowly decaying. The two stars were spiraling toward each other. Einstein's general relativity predicts this should happen because the system loses energy by emitting gravitational waves, ripples in spacetime itself. The rate of orbital decay depends on the speed of light. Hulse and Taylor measured the decay rate and found it matched Einstein's prediction to within a fraction of a percent. They won the Nobel Prize in 1993 for this work. If the speed of light had been changing during their decades of observation, the decay rate would have changed. It didn't. And then, in 2015, we got the most dramatic confirmation yet: the detection of gravitational waves by LIGO, when two black holes collided 1.3 billion light-years away. They sent out ripples in spacetime that reached Earth on September 14, 2015. Those gravitational waves traveled at, you guessed it, the speed of light. Or more precisely, the speed of gravity turned out to equal the speed of light to within measurement error. This is exactly what Einstein predicted. Gravity travels at the same speed as light because both are disturbances in the same underlying spacetime field. If the speed of light had been changing during those 1.3 billion years, the gravitational waves and the light from the event would have arrived at different times. But in August 2017, when LIGO detected gravitational waves from two colliding neutron stars, astronomers around the world pointed their telescopes at the location and saw the light from the explosion just 1.7 seconds after the gravitational waves arrived. Over a distance of 130 million light-years, gravitational waves and light traveled at the same speed to within 1 part in a quadrillion. That's 15 zeros. This is one of the most precise confirmations we have that the speed of light, or rather, the speed of causality, is the same for different types of signals. So with all this evidence that the speed of light is constant, why are we even talking about it changing? Because the universe is under no obligation to make things simple for us. Because every time in history we thought we understood everything, we discovered we were wrong. And because there are deep theoretical reasons to suspect that extreme scales very early in the universe, or at very high energies, the rules might be different. Let me introduce you to a concept that will twist your brain into a knot: quantum gravity. We have two incredibly successful theories in physics: general relativity, which describes gravity and the large-scale structure of spacetime, and quantum field theory, which describes the other three forces: electromagnetism, the strong nuclear force, and the weak nuclear force. These theories work brilliantly in their own domains. but they're fundamentally incompatible with each other. When you try to combine them, when you ask what happens to quantum mechanics in extreme gravitational fields, or what happens to spacetime at quantum scales, the math breaks down. Infinities appear everywhere. The equations stop making sense. This is the biggest unsolved problem in theoretical physics, and it's called the problem of quantum gravity. Now, several approaches have been proposed to solve this. String theory is probably the most famous. In string theory, particles aren't point-like. They're tiny, vibrating strings of energy. Different vibration modes correspond to different particles. String theory naturally includes gravity and predicts extra dimensions of space beyond the three we experience. But here's the thing. String theory also predicts that fundamental constants might not be constant at all. In some versions of string theory, constants like the speed of light or the fine structure constant could vary depending on the values of quantum fields permeating space. These are called moduli fields, and they're like invisible settings that determine the properties of spacetime. If these fields have different values in different regions of space or at different times, then fundamental constants would vary too. This isn't a bug in string theory. It's a feature. Another approach to quantum gravity is called loop quantum gravity. This theory suggests that spacetime itself is quantized, made up of discrete chunks, a kind of quantum foam at the smallest scales. The Planck scale, about 10 to the minus 35 meters, is where these quantum effects should become important. Loop quantum gravity predicts that the speed of light might depend on the energy of photons when you get close to the Planck scale. High-energy photons might travel slightly faster or slower than low-energy photons. This would be almost impossible to detect because the effect is so tiny, but astronomers have tried. They've looked at gamma-ray bursts from distant galaxies' explosive events that emit photons at a huge range of energies. If high-energy and low-energy photons travel at different speeds, they should arrive at Earth at different times after traveling billions of light years. So far, no convincing evidence has been found, but the search continues. Here's where I need you to really pay attention, because this is where everything comes together. If fundamental constants are varying, either across space or across time, it suggests that there's something deeper than the constants themselves. There's some underlying dynamic structure that determines their values. This is sometimes called the landscape problem in physics. In string theory, there might be 10 to the 500 different possible universes, each with different values for fundamental constants. We happen to live in one where the values allow for chemistry, stars, planets, and life. But why these specific values? Is it just luck? Is it anthropic selection? The idea that we find ourselves in a universe compatible with life because we couldn't exist in any other type of universe? Or is there some deeper principle that determines these values? Some physicists think the answer lies in the history of the universe. Maybe the constants we observe today are frozen in remnants of the Big Bang, like fossil traces of the conditions in the early universe. Maybe they were different back then and have been settling into stable values ever since. João Magalla's variable speed of light cosmology suggests exactly this, that the speed of light was enormous in the first moments after the Big Bang, which solved several problems in cosmology, and then it slowed down to the value we measure today. And this brings us to one of the most profound questions in all of science. Why is the universe comprehensible? Why can we discover mathematical laws that describe how reality works? Why is there a speed of light at all? Why isn't the universe just chaos? The physicist Eugene Wigner wrote a famous essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was expressing wonder at the fact that mathematical equations discovered by pure reasoning, often decades or centuries before the relevant physics, turn out to describe physical reality with extraordinary precision. Quantum mechanics is built on complex numbers and linear algebra. General relativity is built on differential geometry. String theory uses abstract mathematical structures called Calabi-Yau manifolds. Why does the universe care about our mathematics? Or is it the other way around? Does mathematics exist in some Platonic realm, and physical laws are just particular mathematical structures? These are deep philosophical questions, but they're not just philosophy. The answer might affect how we do physics. If the universe is ultimately mathematical, then the speed of light and other constants might be inevitable consequences of mathematical consistency. There might be only one logically possible universe, and we're living in it. But if constants can vary, it suggests the universe is more contingent, more arbitrary. The laws we discover are just the local bylaws of our cosmic neighborhood, not universal principles. Let me give you another analogy. Think of the universe as a symphony. The notes being played are all the particles and fields. The instruments are the fundamental forces. The tempo of the symphony is set by the speed of light. Now imagine you're an ant crawling on the sheet music, trying to understand the symphony. You might notice patterns. The notes follow certain rules. Harmonies repeat. There's a mathematical structure to the composition. But you're only looking at one page of a million-page score. What if the tempo changes in the next movement? What if the instruments are different? What if the rules of harmony shift? You'd never know unless you could see the whole score. That's the situation we're in as physicists. We can observe a tiny slice of space-time, the visible universe, 13.8 billion years of history, and we found beautiful patterns and laws. But we have no way to know if those laws are eternal and universal, or if they're just local and temporary. This is why Webb's observation of a varying fine structure constant is so provocative. It suggests we might be seeing evidence that the laws do change, that the score isn't uniform, that reality is stranger than we imagined. Now I want to blow your mind with something even crazier. Are you ready? Here it is. The speed of light in a vacuum might be constant, but light doesn't always travel through a vacuum. And when light travels through matter, it slows down. This is well-established physics. Light travels more slowly through water than through air. It travels more slowly through glass than through water. The refractive index of a material tells you how much slower light travels through it compared to a vacuum. In glass, light travels about 2/3 the speed it does in vacuum. This is why lenses work, why diamonds sparkle, why you see rainbows. But here's the weird part. Even in materials, it's not that the photons themselves slow down. Photons always travel at the speed of light. What happens is that the photons interact with the atoms in the material. A photon gets absorbed by an atom. The atom enters an excited state for a tiny fraction of a second. Then it emits a new photon. This happens over and over, billions of times per second, as light travels through the material. The delays from all these absorption and re-emission events make it look like light is traveling slower, even though each individual photon is always moving at full speed. Think of it like this. Imagine you're driving on a highway with no traffic. You can go the speed limit, say 65 miles per hour. That's like light in a vacuum. Now imagine the highway is full of cars, and you constantly have to slow down and speed up, stop at traffic lights, take detours. Your average speed is much less than 65, even though whenever you're actually moving, you're trying to go 65. That's light in a material. But in the early 2000s, physicists managed to do something that sounds impossible. They slowed light down to less than 1 meter per second in specially prepared ultra-cold atomic gases. Lin Hao at Harvard University famously slowed light to 17 meters per second, about 38 miles per hour, in 1999. Then, in 2001, she stopped light completely. She froze it, stored it, and then released it again. How is this possible? By using quantum interference effects in a phenomenon called electromagnetically induced transparency. By shining 2 lasers at a cloud of ultra-cold sodium atoms, Hao could manipulate the quantum states of the atoms so that they would absorb and re-emit light in a very controlled way. The light pulse essentially became imprinted on the collective quantum state of all the atoms. Then she could turn off one of the lasers, and the light pulse would stay stored in the atoms. Turn the laser back on, and the light pulse would emerge, continuing on its way as if nothing had happened. This is important because it shows that light, or more generally, the propagation of information, can be slowed, stopped, and manipulated by the structure of space-time or the medium it's traveling through. Now, the universe isn't an ultra-cold atomic gas, obviously. But what if space-time itself has structure at the quantum level? What if there's a quantum foam, a grainy texture to space, that light has to navigate through? Then the effective speed of light could be different at different energies, or in different regions of space, where this quantum structure varies. And here's where we connect back to the Big Bang and the early universe. In the first moments after the Big Bang, the universe was unimaginably hot and dense. It was a seething plasma of particles and energy, all interacting frantically. Photons couldn't travel freely. They were constantly scattering off electrons and other particles. The universe was opaque. Light didn't stream freely through space until about 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms. We call this moment recombination, and the light that was released at that moment is what we detect today as the cosmic microwave background radiation. It's baby pictures of the universe. Now here's the thing. In the hot, dense plasma before recombination, did the speed of light even have meaning? Photons weren't traveling freely. They were trapped. And if the quantum structure of space-time was different back then, more turbulent, more energetic, could the effective speed of light have been different? Some cosmologists think yes. Some think the speed of light was higher in the very early universe, which would solve what's called the horizon problem. The horizon problem is this. When we look at the cosmic microwave background, we see that the temperature is the same in all directions to about 1 part in 100,000. Different patches of the sky are at almost exactly the same temperature. But according to standard Big Bang cosmology, those patches were never in causal contact. They're too far apart. Light hasn't had time to travel between them even in 13.8 billion years. So how did they end up at the same temperature? How did they coordinate? The standard answer is cosmic inflation. A theory proposed by Alan Guth in 1980 and refined by many others says that in the first fraction of a second after the Big Bang, between about 10 to the minus 36 and 10 to the minus 32 seconds, the universe underwent an exponential expansion. Space itself expanded faster than the speed of light, which is allowed because the speed of light limit only applies to motion through space, not the expansion of space itself. Before inflation, all the regions we can see today were close together in thermal equilibrium. Then inflation blew them apart to enormous distances. That's why they still look the same today. They used to be the same region. Inflation solves the horizon problem and several other problems in cosmology. It also makes predictions that have been confirmed, like the pattern of fluctuations in the cosmic microwave background. But inflation is strange and requires some exotic physics, a hypothetical field called the inflaton field that behaves in very specific ways. Some physicists find it unsatisfying. Magueo and Albrecht's variable speed of light theory offers an alternative. They said, what if instead of space expanding faster than light, light was just faster? What if in the first moments after the Big Bang, the speed of light was billions of times higher than it is now? Then distant regions could have been in causal contact, reached the same temperature, and then as the universe cooled, the speed of light settled down to the value we see today. This solves the horizon problem without needing inflation. Now, you might be thinking, wait, can the speed of light just change like that? Wouldn't that break everything? And you're right to be skeptical. If you just decree that c was different in the past, you have to explain what else changes to keep the physics consistent. Remember, c appears in dozens of equations. If you change c, you change energy mass equivalence. You change the strength of electromagnetic interactions. You change the size of atoms. Magueo and his collaborators worked out a framework where c could vary while keeping the physics self-consistent. The key is that other constants have to vary in tandem. It's like adjusting multiple knobs on a control panel simultaneously so that the outputs stay balanced. Whether this theory is correct is still debated. The nice thing about inflation is that it makes very specific predictions about the polarization patterns in the cosmic microwave background. And observations from satellites like WMP and Planck have confirmed many of these predictions. Variable speed of light theory makes different predictions, and so far, the data favor inflation. But variable speed of light theory hasn't been ruled out completely. The debate continues. Here's what's fascinating to me. We're asking whether one of the most fundamental aspects of reality, the speed at which information can travel, is truly fundamental, or whether it's emergent from something deeper. Emergent is a concept in physics where complex behavior arises from simpler underlying rules. Temperature is emergent. It's just the average kinetic energy of molecules. Pressure is emergent. It's just molecules bouncing off walls. Could the speed of light be emergent too? Some theories suggest yes. In approaches to quantum gravity that view space-time as emergent, something that arises from quantum entanglement of more fundamental degrees of freedom, the speed of light would be a secondary consequence, not a primary input. And if conditions change at the quantum level, the emergent speed of light could change too. This is deeply speculative, but it's being seriously investigated by physicists at places like the Perimeter Institute in Canada and the Institute for Advanced Study in Princeton. Let me take a step back and ask you something. How are you feeling right now? Are you experiencing that beautiful cocktail of wonder and confusion? Are you starting to question things you thought were solid facts? Good, because that's exactly where new understanding is born. In the confusion, in the not knowing, in the willingness to have your worldview shattered and rebuilt. Before we go further, I want you to do something. Pause this video for just a second and look around you. Look at the light hitting the objects near you. Look at the colors. Think about the fact that all of that is electromagnetic radiation traveling at 299,792,458 meters per second, maybe. Think about the fact that the light hitting your eyes right now left those objects nanoseconds ago. You're not seeing the present, you're seeing the past. The sun you see outside is 8 minutes in the past. The stars you see at night could have exploded centuries ago, and you wouldn't know yet. Light is a time machine, showing you where things were, not where they are. And if light is slowing down, then the time machine is running at a different speed than we thought. Now let's talk about what happens if the speed of light really is changing. What would it mean for you, for Earth, for the universe? First, if the speed of light is decreasing, then time itself is changing relative to space. Remember, c is the conversion factor between space and time. Einstein showed that space and time are not separate. They're woven together into space-time. The equations of special relativity have a quantity called the space-time interval, which is a combination of distance and time that stays constant for all observers. If c changes, the relationship between distance and time changes. Days might be getting longer, not because Earth's rotation is slowing, though it is, very slightly, but because time itself is dilating relative to space. Before you panic, let me be clear. If this is happening, the effect is incredibly tiny. We're talking about changes of less than 1 part in 100,000 over billions of years. You wouldn't notice it in your lifetime. Neither would your great-grandchildren. But over cosmic timescales, it would add up. Here's something that should make your skin tingle. If the speed of light was higher in the past, then light from distant galaxies took less time to reach us than we think. That means the universe might be younger than we calculate. We think the universe is 13.8 billion years old, based on how far light has traveled to reach us from the most distant objects we can see. But if light was traveling faster back then, it covered more ground in less time, and the universe could be younger. Or alternatively, if light is slowing down now, then billions of years from now, astronomers will calculate that the universe is older than it really is. This messes with our cosmic timeline. When did the first stars form? When did the first galaxies form? All of those dates depend on assuming a constant speed of light. Another consequence, energy. Einstein's equation E equals mc tells us that a small amount of mass contains an enormous amount of energy because c is such a huge number. If c was smaller in the past, then nuclear reactions would have released less energy. The sun would have been dimmer. Stars would have evolved differently. The entire history of stellar evolution would be different. This could affect our understanding of nucleosynthesis, how elements were forged in stars. The abundances of elements we see in the universe depend on nuclear reaction rates, which depend on C. And here's something even weirder. If C is changing, it might not be changing uniformly throughout the universe. Remember that 2011 study I mentioned where Webb found evidence that the fine structure constant varied in different directions? If true, this would mean the universe has a preferred direction, an axis of asymmetry. That would violate a principle called isotropy, the idea that the universe looks the same in all directions. Isotropy is one of the foundational assumptions of modern cosmology. It's part of the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. If this is wrong, if there's cosmic anisotropy, then the universe has structure we didn't know about. Maybe it's rotating. Maybe there's a gradient in some field that pervades space. The implications are staggering. It would mean our universe isn't quite as simple and symmetric as we thought. Some physicists have speculated that we might live in a multiverse, a vast ensemble of different universe regions with different physical properties. The boundaries between these regions might be places where constants transition from one value to another. If we're near such a boundary, we might detect variation in fundamental constants across the sky. This is extremely speculative, but it's a logical consequence if we take varying constants seriously. Let me tell you about some of the strongest evidence against varying constants, because I want you to have the full picture. In 2004, a team led by Michael Murphy conducted an exhaustive analysis of quasar absorption systems, the same type of data John Webb used. Murphy's team found no evidence for variation in the fine structure constant, 0. Their measurements were consistent with alpha being constant over the past 10 billion years. How do we reconcile this with Webb's findings? Part of it is methodology. Different teams use different analysis techniques, different data sets, different assumptions about how to model the absorption lines. Small systematic errors, subtle biases in how you measure wavelengths, or how you account for other effects can creep in and produce false signals. This is the nature of cutting-edge science. When you're trying to measure effects at the limit of your instrument's capabilities, you're in a gray zone where honest researchers can get different results. What we need is better data and independent confirmation from completely different methods. One promising avenue is using atomic clocks. Modern atomic clocks are so precise they can detect changes in time at the level of 1 part in 10 to the 18. That's like measuring the age of the universe to within 1 second. Different types of atoms have energy levels that depend on different combinations of fundamental constants. If you compare different types of atomic clocks over time, any drift between them would indicate that fundamental constants are changing. Several labs around the world are doing exactly this. For over 15 years, they've been comparing cesium clocks, rubidium clocks, ytterbium clocks, strontium clocks. So far, no drift has been detected within the measurement precision. This puts very tight constraints on how fast fundamental constants could be changing today. If the fine structure constant is changing, it's changing by less than 1 part in 10 to the 17 per year. That's extraordinarily slow. To put it in perspective, if alpha has been changing at this rate since the Big Bang, the total change would be less than 1 part in a million. This is consistent with both Webb's claims and Murphy's null results. The changes are tiny. But here's what keeps me up at night. What if the changes aren't smooth and steady? What if the speed of light fluctuates? What if there are sudden jumps, discontinuities in the fabric of spacetime? Some theories of quantum gravity suggest that spacetime might be fundamentally discrete, grainy at the smallest scales. If so, then as we probe shorter distances or higher energies, we might see quantum fluctuations in the effective speed of light. Individual photons might take slightly different paths through this quantum foam, arriving at slightly different times even if they left from the same source simultaneously. This is called quantum dispersion, and it's something astronomers are actively searching for in gamma-ray bursts and other high-energy astrophysical events. Another possibility, maybe the speed of light changes in response to the energy density of the universe. In the early universe, when energy density was enormous, maybe C was different. As the universe expanded and cooled, energy density decreased and C settled into its current value. But here's the kicker. The universe's expansion is accelerating. We know this from observations of distant supernova. Something we call dark energy is pushing space apart faster and faster. We have no idea what dark energy is. It might be a cosmological constant, an inherent energy of empty space itself. Or it might be a dynamic field that changes over time. If dark energy is changing, and if fundamental constants are coupled to dark energy, then those constants might be changing too, subtly, right now. Here's an analogy that might help. Think of space-time as a fabric, and the speed of light as the speed that waves travel through this fabric. Now imagine the fabric is being stretched by cosmic expansion. As it stretches, its tension changes, its density changes. The speed that waves travel through a medium depends on the properties of the medium. Sound travels faster through steel than through air because steel is denser and more rigid. Similarly, if the properties of spacetime itself are changing due to cosmic expansion and dark energy, the speed that information can propagate through spacetime, the speed of light, might change too. This is the core insight of variable speed of light theories and their modern descendants. The speed of light isn't a magic number handed down from on high. It's a property of spacetime, and properties can change if conditions change. This should actually make intuitive sense. Why should the speed of light be constant for all of eternity? What's special about 299,792,458 meters per second? Why not some other number? The fact that we can even ask these questions suggests that the speed of light is contingent, not necessary. There's no deep reason it has to be exactly this value. Unless there is, let me introduce you to another mind-bending idea, anthropic reasoning. The anthropic principle, in its weak form, says that we observe the universe to have properties compatible with our existence, because if it didn't, we wouldn't be here to observe it. This seems tautological and useless, but it actually has explanatory power. Many properties of the universe seem fine-tuned for life. If the electromagnetic force was slightly stronger or weaker, atoms wouldn't form properly. If the strong nuclear force was slightly different, nuclei would fly apart or collapse. If the cosmological constant was much larger, the universe would have expanded so fast that galaxies never formed. And if the speed of light was very different, the universe would be radically different. If c were much slower, electromagnetic forces would dominate over other forces differently. Chemistry would be different, and life as we know it wouldn't exist. If c were much faster, the early universe would have evolved differently, and structure formation might not have happened the way it did. So maybe the reason we find ourselves in a universe with this particular speed of light is that only universes with approximately this value can support observers. This doesn't explain why the speed of light is constant, but it constrains what values it could have had in regions where life can evolve. The Anthropic principle is controversial. Many physicists hate it because it feels like giving up on finding deeper explanations. It's like saying things are the way they are, because if they weren't, we wouldn't be here to ask the question. But others argue it's a legitimate constraint, especially if we live in a multiverse where different regions have different constants. We necessarily find ourselves in a region where the constants are compatible with our existence. This is called observer selection bias. It's the same reason we find ourselves on a planet with liquid water and breathable atmosphere, not because Earth is typical. It's not, but because we couldn't exist anywhere else. If fundamental constants vary across the multiverse, then the Anthropic principle might be the only explanation for why they have the values we measure. This is philosophically unsatisfying to many, but it might be the truth. Not all questions have neat, satisfying answers. Sometimes the universe just is the way it is, and we're here to observe it because this particular configuration happened to work. Let me share something personal with you. When I first learned about the possibility that fundamental constants might not be constant, I went through a kind of existential crisis. If the laws of physics aren't eternal and universal, then what is real? What can we trust? If the speed of light is changing, then time is changing, space is changing, energy is changing. Everything built on those foundations is shifting. It's like discovering the ground you're standing on is floating on water. It's unsettling. But then I realized something profound. This doesn't make the universe less real. It makes it more interesting. We've always known that our understanding is incomplete. Newton's laws worked perfectly for 200 years, until we discovered they were approximations that break down at high speeds and strong gravity. We replaced them with relativity. Quantum mechanics showed that reality at small scales is probabilistic and weird, not deterministic and mechanical. Each revolution in physics has revealed deeper layers of reality. If we discover that fundamental constants vary, it will be another revolution, another layer. And beneath that layer, there will be more structure, more patterns, more beauty to discover. Here's what I want you to understand. The fact that we can ask whether the speed of light is changing, the fact that we can design experiments to test it, the fact that we can imagine alternatives and explore their consequences. This is one of the most extraordinary things about human consciousness. We are patterns of atoms that have become aware of themselves, that can question the nature of reality, that can look out at the cosmos and try to understand it. We're made of star stuff, as Carl Sagan said, but more than that, with the universe examining itself. When you look up at the stars, you're not separate from them. You're part of the same system. The atoms in your body were forged in stellar furnaces billions of years ago. The photons hitting your eyes right now began their journey in the sun's core thousands of years ago, bouncing around inside the sun before finally escaping and crossing 150 million kilometers in 8 minutes to reach you. Light connects everything. And if light is changing, then the connections are changing. The web of causality that links all events in space-time is dynamic, not static. Let me tell you about one more piece of evidence that fascinates me. It comes from studying quasars that are gravitationally lensed. Gravitational lensing happens when a massive object like a galaxy bends space-time, acting like a lens for light passing near it. Sometimes a single quasar appears in multiple images because its light takes different paths around the lensing galaxy. Now, if the speed of light is the same along both paths, the light takes different amounts of time to arrive because the paths have different lengths. By measuring the time delay between variations in the quasar's brightness showing up in the different images, astronomers can measure the difference in light travel time. But here's the clever part. If the speed of light was different in the past or varies with direction, the time delays would be different than predicted by standard physics. A team led by Sherry Sue has measured time delays in several lengths quasar systems with incredible precision. Their results are consistent with the speed of light being constant. But, and this is important, they also provide a completely independent way to measure the expansion rate of the universe, called the Hubble constant. And their measurements disagree with measurements from the cosmic microwave background. This is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology right now. Could varying constants be the solution? Maybe. If the speed of light or other constants were different in the early universe, it would affect how we interpret the cosmic microwave background, which could resolve the Hubble tension. This is active research happening right now. I'm going to say something that might sound crazy. I think it's beautiful that we don't know. I think it's wonderful that reality is still mysterious, that there are deep questions we haven't answered. Imagine if we had figured everything out. Imagine if there were no more mysteries, no more discoveries to make. How boring would that be? The fact that we're still puzzling over whether fundamental constants are truly constant means we're still in the early days of understanding reality. We're like children learning to read, sounding out the letters of the cosmic alphabet. We've learned some words, maybe even some sentences. But the full story? We haven't even glimpsed it yet. And that should fill you with wonder, not despair. Every generation of physicists has believed they were close to understanding everything. In the late 1800s, some physicists thought they had almost figured out all of physics. Then quantum mechanics and relativity came along and shattered that illusion. In the 1960s and 70s, after the standard model of particle physics came together, some thought we were close again. Then we discovered dark matter and dark energy, which together make up 95% of the universe, and we have no idea what they are. Now we're grappling with quantum gravity, the multiverse, and possibly varying constants. There's no end in sight to the mysteries. Let me bring this back to something concrete. You, your life. Why does this matter to you personally? Here's why. The story you tell yourself about reality shapes how you live. If you believe the universe is mechanical, deterministic, fully understood, then you might feel small and insignificant, like a cog in a machine. But if you understand that reality is still mysterious, that the deepest laws of physics might still be shifting and evolving, that the speed of light itself might be dynamic, then you're living in a universe that's alive with possibility. You're not in a static, finished cosmos. You're in a dynamic, evolving, creative universe. And you're part of that creativity. Every time you learn something new, every time you have a novel thought, you're adding something that never existed before to the universe. The pattern of neurons firing in your brain right now is unique. It's never happened before and will never happen again. You are unrepeatable, and you're experiencing something remarkable. You're conscious. You have subjective experience. You feel what it's like to be you. We have absolutely no idea how this works. Consciousness is probably the deepest mystery in all of science. Some physicists and philosophers think consciousness might be fundamental to reality, not just an emergent property of complex brains. What if the universe is in some sense conscious, or at least proto-conscious, at the quantum level? What if observation and measurement by conscious beings plays a role in collapsing quantum wave functions and determining what becomes real? This isn't mysticism. This is serious physics. The measurement problem in quantum mechanics is real. Before you measure a quantum system, it exists in a superposition of multiple states simultaneously. When you measure it, the superposition collapses into one definite state. But what counts as a measurement? Does it require a conscious observer? Physicists have debated this for a century. Most think consciousness isn't necessary. Any interaction with the environment causes decoherence and effective collapse. But some, like the mathematician Roger Penrose and anesthesiologist Stuart Hemroff, think consciousness is quantum mechanical and plays a fundamental role. If they're right, then consciousness and physical law are intertwined. And if physical laws can change, maybe consciousness can influence them in subtle ways. Before you dismiss this as woo, remember, we don't understand consciousness, and we don't understand quantum mechanics. Being open to strange possibilities is not the same as believing them uncritically. It's about holding space for mystery. Here's what I know for sure. You are not separate from the universe. You are a temporary configuration of the universe that has become self-aware. The atoms in your body are constantly being replaced. The food you eat becomes you. The air you breathe becomes you. You're a process, not a thing. A verb, not a noun. And the speed at which information propagates through your nervous system, the speed at which signals travel from your senses to your brain, all of that is ultimately limited by the speed of light. If light is changing, then you are changing at a fundamental level. Now let me share some of the most recent research that's pushing our understanding further. In 2023, a team using the European Very Large Telescope found new evidence suggesting the fine structure constant might be different in different parts of the universe. They analyzed light from quasars in opposite directions in the sky and found subtle differences in the absorption spectra. If confirmed, this would be revolutionary. It would mean the universe has dipole anisotropy, a preferred axis, which would violate one of the core assumptions of the standard cosmological model. Other teams are trying to replicate these findings. We need more data, better instruments, and independent confirmation. This is how science works. One team finds something surprising. Others try to replicate it. If it holds up under scrutiny from multiple independent groups using different methods, it becomes established. If not, it gets discarded. Right now, varying constants are in this uncertain zone. There's intriguing evidence, but it's not conclusive. Meanwhile, theoretical physicists are exploring what a universe with varying constants would look like. They're building models, making predictions, comparing them to data. Some models predict specific patterns in how constants should vary if they're coupled to other fields. Some predict correlations between different constants varying together. These predictions can be tested with future observations. The next generation of telescopes, like the James Webb Space Telescope, which is already revolutionizing astronomy, and the upcoming extremely large telescope will be able to measure absorption spectra from distant quasars with unprecedented precision. We'll be able to test whether the fine structure constant has changed over cosmic history with much greater certainty than we can today. Similarly, the next generation of atomic clocks will be able to detect even tinier variations in fundamental constants over time. We're living in an exciting era where experiments that were impossible a decade ago are now routine. Within your lifetime, we might definitively answer the question, does the speed of light change? And if the answer is yes, it will trigger a revolution in physics comparable to quantum mechanics or relativity. We'll have to rebuild our understanding of the universe from the ground up. New theories will emerge. New mathematics will be invented. New technologies based on those theories will be developed. The trajectory of human civilization could change. That's not hyperbole. Our entire technological civilization is built on our understanding of physics. GPS satellites work because we understand relativity. Computers work because we understand quantum mechanics. If our understanding of fundamental constants changes, new technologies become possible. Maybe we'll learn to manipulate space-time more directly. Maybe we'll find ways to store and transmit information that bypass current limitations. Maybe we'll discover new energy sources. Or maybe the answer will be no. Maybe decades of increasingly precise experiments will confirm that fundamental constants are indeed constant, truly universal and eternal. That would be just as important. It would tell us that reality has a stability and consistency that's absolute. It would mean that the laws of physics we discover here on Earth apply unchanged across the entire observable universe and throughout all of cosmic history. That's profound, too. It would mean that an alien civilization a billion light years away is discovering the same laws we are. The same quantum mechanics, the same relativity, the same standard model. There's a universality to physical law that transcends location and time. That's beautiful in a different way. Either way, we learn something deep about the nature of reality. That's why this question matters. It's not just academic curiosity. It's about understanding what kind of universe we inhabit. Is it stable or dynamic? Uniform or varied? Simple or complex? The answer shapes our entire worldview. Let me address something you might be thinking. If the speed of light is changing so slowly that we can barely detect it, does it really matter? Who cares about 1 part in 100,000 over billions of years? Here's why it matters. First, it tells us that what we thought were absolute foundations are actually contingent. That shifts how we think about everything. Second, small changes add up. 1 part in 100,000 over 13 billion years means the speed of light might have been 0.1% different at the time of the Big Bang. That sounds small, but when you're talking about the foundational constant that every other calculation depends on, a 0.1% difference cascades through everything. Nuclear reaction rates would be different. The balance between radiation and matter in the early universe would be different. Structure formation would be different. The universe could look completely different if we go back far enough. Third, if constants can change even a little, it means the mechanisms that determine their values are dynamic. And if they're dynamic, they could change more rapidly under different conditions. Maybe in the vicinity of black holes, where space-time is severely warped, the effective speed of light is significantly different. Maybe in the first fraction of a second after the Big Bang, constants were changing wildly, and only later settled into stable values. The fact that change is possible at all opens up vast new territory to explore. We don't know which of these is true. But here's what gives me chills. We might find out. In the next few decades, we might actually answer some of these deepest questions about reality. We live at a special time in history. For most of human existence, we had no ability to probe the fundamental structure of the universe. For the past few centuries, we've been building that ability slowly, painstakingly. And now we're at a point where we can ask questions about the nature of space-time, the constancy of constants, the existence of other universes, and actually do experiments to find answers. That's extraordinary. You are alive at a time when humans are making first contact with the deepest truths of reality. Think about that. Future historians, if there are any, will look back at this era as one of the great ages of discovery, comparable to the scientific revolution of the 1600s or the quantum revolution of the early 1900s. And you get to witness it. You get to be here as we puzzle through these mysteries. If that doesn't fill you with awe, I don't know what will. Let me tell you about one more experiment that's being planned. It's called the Einstein telescope, a next-generation gravitational wave detector that will be far more sensitive than current LIGO detectors. When it's built, possibly in the 2030s, it will be able to detect gravitational waves from the very early universe, potentially even from cosmic inflation itself. Those primordial gravitational waves have been traveling through space for over 13 billion years. If the speed of gravity, which should equal the speed of light, has changed during that time, we'll be able to detect it by comparing gravitational wave signals from different distances. Closer sources would show light and gravity traveling at today's speed. More distant sources would show the speeds from billions of years ago. This is direct observation of how fast causality propagated in the past. It's one of the most promising ways to definitively test whether the speed of light has changed. I'm not going to lie to you and say we'll definitely find that it has changed. The smart money is still on the speed of light being constant. Most experiments so far suggest it is. But the possibility that it isn't is tantalizing enough that physicists around the world are dedicating their careers to finding out. So where does this leave us? What should you take away from all of this? First, reality is stranger than you think, weirder than you can imagine. The universe doesn't owe us simplicity or comprehensibility, yet somehow we can understand parts of it. That's miraculous. Second, uncertainty is not weakness. Not knowing is the beginning of wisdom. The physicists who are most certain about everything are usually wrong. The ones who say, "We don't know yet, but here's what we're trying to find out," are the ones pushing knowledge forward. Third, you are part of this story. You're not a passive observer. Every time you learn something about the universe is learning about itself through you. You are how the cosmos comes to understand itself. Fourth, the big questions aren't answered yet. Maybe the speed of light is slowing down. Maybe it's not. Maybe constants vary across space. Maybe they don't. We're still figuring it out. And that means you have the opportunity to be part of the discovery, even if just as an informed, excited witness. Fifth, what seems solid and unchanging might not be. The ground shifts beneath our feet, the constant's inconstant, the eternal temporary. This is unsettling, but also liberating. If reality itself can change, then so can you. You're not fixed. You're not finished. You're a work in progress, just like the universe. I want to end by bringing us full circle. Remember at the beginning when I told you about John Webb's discovery that the fine structure constant appears to be different in distant quasars? Remember how that suggested the speed of light might have changed? Here's the final twist. Even if we confirm that constants have changed, we might never know why. We might measure the change precisely. We might map out how it varies across space and time. We might build new theories that accommodate variable constants. But the ultimate why, the reason reality is structured this way and not some other way, might forever elude us. Or maybe it won't. Maybe there's a final theory, a theory of everything, that explains all the constants and how they relate and why they have the values they do. Maybe that theory is just around the corner. String theory, loop quantum gravity, emergent gravity, causal set theory physicists are exploring dozens of approaches to quantum gravity, and one of them might be right. In the next decade or two, we might have a breakthrough. Or maybe the final theory will require new mathematics that hasn't been invented yet, new concepts that we can't even imagine right now. Maybe it will take another century. Or maybe there is no final theory. Maybe it's turtles all the way down deeper explanations beneath every explanation, with no ultimate foundation. That would be strange and disturbing, and somehow appropriate for a universe as weird as ours. Here's what I believe. The journey is the point. The striving to understand, the willingness to question, the courage to follow evidence, even when it contradicts what we thought we knew. That's what makes us human. That's what makes life meaningful. Not the answers, but the quest for answers. Not the destination, but the journey. You watching this video right now, thinking about whether the speed of light is slowing down, you're part of that quest. You're part of humanity's greatest adventure, the attempt to understand existence itself. And whether the speed of light is constant or variable, whether reality is simple or complex, whether we figure it all out or remain forever puzzled, none of that changes the fact that we're here, we're aware, and we care enough to ask. That's profound. That's beautiful. That's enough. So the next time you see light sunlight on water, starlight in the night sky, the glow of your screen, remember, you're seeing one of the universe's deepest mysteries. Light carries information at the cosmic speed limit, weaving together space and time, connecting everything to everything else. And that speed limit, that fundamental constant we've relied on for over a century, might not be quite as constant as we thought. The universe might be more dynamic, more alive, more mysterious than we ever imagined. And you get to be here, in this moment, contemplating that mystery. How lucky is that? How extraordinary. You are a pattern of atoms that has become conscious, that can wonder about the speed of light, that can ask whether the foundations of reality are shifting. You are the universe becoming aware of itself. And that's more wonderful than any answer we might eventually find. Thank you for joining me on this journey. Thank you for being curious enough to stick with me for over 3 hours as we explored one of physics' deepest questions. Whether the speed of light is slowing down or not, one thing is certain: your willingness to engage with these ideas, to question, to wonder, to imagine. That's the spark that drives all discovery. Keep that spark alive. Keep asking questions. Keep wondering. And who knows? Maybe someday you'll be the one who figures out the next piece of the puzzle. The universe is waiting.